Hello, everyone. My name is Carlos Arvilla from the National Magnet Lab, and this is Magnet Exploration. So just to introduce you to the Magnet Lab a little bit, the Magnet Lab is one of 7 high magnetic field labs around the world. The other 6 magnet labs are between Europe and Asia, so we're the only magnet lab on this side of the planet. But of all the magnet labs that exist, this one here is the largest and the highest powered. So most scientists in the world come to us because with the magnets we have, we can do things that no one else in the world can do. Now, our #1 job is we're a user laboratory. So we have the magnets so that different users, different scientists from around the world can come to us, use our magnets, do their research, and then go back home. In 2019, we had over 2,000 different user visits, and we're completely funded by the National Science Foundation and the state of Florida. Our budget was $58.8 million, and that's every year. Now, the magnets are free for the scientists to use. We don't charge them on the condition that they're going to share their research. So if they share the research with everyone else, either by writing a publication in a journal, such as the Journal of Magnetism and Magnetic Material, the Journal of Magnetic Resonance Imaging, or Nature, the research for them is completely free and covered by the Magnet Lab. But there are a lot of different fields of science that we do more than just magnets. We do material science, engineering, geology, paleontology, physics, chemistry, biology, and many, many more. Now, we are one magnet lab, but we actually have 3 different site locations. We have the main site in Tallahassee, Florida at Florida State University. We have a site in Gainesville, Florida at the University of Florida. And we also have labs at Los Alamos National Laboratory in Los Alamos, New Mexico. Since we are taxpayer funded by the National Science Foundation and the state of Florida, that makes all taxpayers stakeholders in our facility. So on behalf of all of us, thank you for supporting our science. Now let's talk a little bit about magnets. What is magnet? A magnet is a material that attracts, has a north pole and south pole, and a magnetic field. This is a magnet, but this is also a magnet. This is a magnet too, and even this one's a magnet. And guess what? This is a magnet too. All of these here are different types of magnets and they work differently, but they all have the same rules. When we talk about magnets, we got 2 different types of magnets. We have permanent magnets, and a permanent magnet is what you think of when you think of a traditional magnet. Refrigerator magnets, magnets that are on your toys, and calendar magnets. These are all different types of permanent magnets. Now we also have temporary magnets, and temporary magnets are things like staples, paper clips, the refrigerator door, car door, screws, nails, hammers, screwdrivers, scissors, and even electromagnets. Temporary magnets are objects that are not magnets all the time, but they can be magnetized and they can hold a magnetic field. Now here's a picture of a magnet. There are some things that all magnets, regardless of permanent or temporary, all magnets have certain properties. And the first property that all magnets have is that all magnets have poles. They have a north pole and they have a south pole. And if you take those 2 magnets, and let me show you here with the magnets that I've got here, if you take those 2 magnets and you put the 2 north poles next to each other, they're going to repel. But if you put the opposite poles next to each other, they're going to attract. So let me show you that. Here are my magnets, and you can see I've got the north pole colored red and the south pole colored purple. And if I bring them close to each other, they will actually attract to each other just like this. But if I bring the same pole next to each other, in this case, south against south, they're going to push against each other and they're not going to attract. This is called repelling. And the reason that magnets can attract and repel is because of what is around them. This is something that is around all magnets, and we call this the magnetic field. All magnets have a magnetic field, and that magnetic field has a direction. It is actually moving from the North Pole to the South Pole. So you can see here in this picture that the field is moving from the north and into the south, again, from the north into the south, and that's what all fields do. And this is important because this is the reason that magnets can attract to each other. When you bring opposite poles next to each other, like north and south, they're going to attract, and those fields are going to line up in the same way, and the magnets are going to come together. But when magnets repel, those 2 fields are going to be pushing against each other, so they're going to push away from each other like this. So So the reason that magnets attract and repel is because of the magnetic field. Now, can you feel a magnetic field? Well, we can't, but there are a lot of animals that can. Unfortunately, magnetic fields are invisible to us. We can't see or feel them, but there are a lot of animals in nature that can sense magnetism, like sea turtles, migratory birds, and sharks. I know a lot of animals use the magnetic field to help them navigate from one place to another using Earth's magnetic field as their guide. But there are even some animals that can see a magnetic field. Robins can see magnetic fields, but only out of one eye, the right eye, and using the left half of the brain, and only in very bright settings. So it's very interesting that robins can do this. I love talking about Arctic foxes because these foxes we believe they can also see magnetic fields, but they use Earth's magnetic field to hunt. And if they hunt from a northeast direction and they pounce from that direction, they have a 73% catch rate. But if they hunt from any other direction, they only have an 18% catch rate. Now, we've been watching them and studying them enough to tell you that this is the same regardless of the time of day, the season, the cloud cover, the wind, or the weather. Now, this here is a periodic table of elements. And on this chart are all the elements that make up all the things around us. And I'm going to tell you that this column and this column, this red, this orange, this yellow rectangle here, this green triangle area here, and then these two rows down here, all of those are different types of metal. But not all of them will attract to magnets. In fact, only 3 of them are naturally magnetic. And those 3 are iron, cobalt, and nickel. Now, they're all right next to each other on a periodic table using numbers 26, 27, and 28. Those are their atomic numbers. But there's an easier way to remember what these 3 are. If you like movies like I do, maybe you've seen Monsters, Inc. Well, I don't want you to think about Monsters, Inc. right now. I want you to change a little bit and think about Magnets, Inc. And if you remember Magnets, Inc., you'll always remember Inc. stands for iron, nickel, and cobalt. And that's how you'll remember that those are the 3 naturally magnetic materials. Now, how we measure how strong a magnet is by a unit of measurement called Tesla. So Teslas tell us how strong a magnetic field is. And if you have any magnets on your refrigerator, they're probably going to be about 0.03 Tesla. Now, if you've ever seen a junkyard magnet that they use to move scrap metal around the junkyard, that magnet is 1 Tesla in strength. If anyone's had an MRI before in a hospital, an MRI, magnetic resonance imaging machine, an MRI is an electromagnet as well, and an MRI is 2 to 3 Tesla. And at the Magnet Lab, we have a bunch of different types of electromagnets. But I want to show you these 2. This is the world record, world's strongest water-cooled magnet. And this is the world record, world's strongest continuous field magnet. And these are 2 powerful electromagnets that go up to 45 Tesla. The one down here is 45 Tesla. The one up here is 40. So they're incredibly strong. Now let's talk a little bit about electromagnets like what we have at our lab. What is an electromagnet? An electromagnet is a magnet that needs electricity to work. So if you give it electricity, you turn on the electricity, the magnet works. But when you turn off the electricity, the magnet doesn't work, it is off. Now, what happens if you add more electricity to your electromagnet? Well, if you turn off the electricity, it doesn't do anything. If you turn it on, it works again. And if you give it more electricity, the magnet gets stronger. And that's how we were able to create the world's strongest magnets, by giving them more and more electricity. Let me show you some of these magnets. This here is our 21 Tesla nuclear magnetic resonance, which we call NMR, superconducting magnet. The inside of this magnet has been cooled down to almost 450 degrees below 0 in order to make the electricity flow better through the wires in this electromagnet. Now, the top part of this magnet up here is a helium tank, and the bottom part down here is the magnet. The reason we've got helium, and yes, it's the same helium you put into your balloons, but we've cooled it down and turned it into a liquid. And that liquid is about minus 450 degrees Fahrenheit. So that cold helium comes out of the tank into the magnet and cools it off. These 2 here are helium tanks that we use to refill the helium in the magnet. Now looking at the magnet, there's a couple of lines around it, and these are our warning lines to show us where the magnetic field is from this magnet. Remember, it's a 21 Tesla magnet and it is pretty strong. This down here is our first warning line, and if you cross that first warning line, you don't feel anything. Nothing magnetic is going to be pulled or attracted, but anything that is magnetically recorded will be erased. So if you take your credit cards or your computers across that line, it is going to wipe out all that information. The red line here is our secondary warning line, and this black line is the line of attraction. After you cross this black line, you are in the strongest part of the field where if you're holding paper clips in your hand, they will be pulled right out of your hand towards the magnets. Scientists will go underneath this magnet. They will put their probe into the magnet from the bottom, walk to the back of the room and do their experiment and run their experiment from the back of the room out of the magnetic fields. These two are 25 Tesla resistive magnets. So these magnets are not super cooled, but they do still need to be cooled so that they don't overheat. These two magnets here have electricity surging through them from one side down through the magnet and out the other, and also cold water through them to cool down the magnet and keep it at low temperature so it doesn't overheat. So these resistive magnets work. These are the stronger of the magnets that we have at the lab, and there are chairs up here because the scientists will be sitting on top of the magnet and put their probes in through the top. So the other magnet had the probes going in through the bottom. These magnets, the probe goes in through the top. Just like before, the scientists will set up their experiment and then they'll walk back out of the room and run their experiments from the back of the cells where the magnets are housed. It is not harmful to be in the magnetic field, but it is bad for the computer, so all the computers and electronics are kept out of the magnetism. If the magnets don't get the water to cool down, this is what happens. When the magnets are not able to cool down, they heat up so much that they actually start to melt. Now that's bad for the magnet and we have to replace this when it happens, but it doesn't happen very often because our computers are always checking the temperature, the current, and the water that's going through the magnets to make sure that everything is okay. This is our 36 Tesla series connected hybrid, and this is one of the more important magnets because it gets very strong, 36 Tesla, but it uses a lot less electricity than the other magnets at our lab. You can see that it's got some shielding here to help block part of the field. And this one, like the one before, it will be loaded from the top. So the scientists will go on top of the magnet, put their probe into the middle, and then come back here. And you can see that the computers are in the back of the room outside of the magnetic field. Now, the strongest magnet we have is our 45 Tesla hybrid magnet. And it's called a hybrid magnet because it's actually two different magnets together. The very center of it is the resistive magnet made out of the bitter plates that I showed you. And then the outside is a superconducting magnet. So it's got a resistive magnet in the middle, a superconducting magnet around it, and together they combine in the very center to create a 45 Tesla field. If you have a pacemaker, you are not allowed in this area because the magnetic field could interfere with a pacemaker. You don't bring your credit cards or ATM cards here because, like I told you, they will be erased. And of course, you don't want to bring your computers here either. And this is our certificate from Guinness that shows you that we are record holders for the world's strongest, most powerful artificial magnetic field at 45 Tesla that was created in June of 2000. So we have held that record for quite a long time. This is what happens when you go around the corner. And again, another warning gate that tells you where you can and cannot go. When the magnet is on, only the operators of the magnet and the scientists are allowed in this area. And this is the magnet up here. This large gray cylinder that you see up there, that is the superconducting part of the magnet. And this part underneath it, that is supplying the water and the electricity to the resistive part in the middle of the magnet. There is a helium tank over here that supplies the liquid helium to the superconducting part of the magnet. Here's another picture of that. Again, here's your superconducting magnet. Here's the water and electricity for the resistive part. And this is the floor. And the floor has to be very solid to make sure that the magnets are operating properly. So this is the floor that is 3 feet thick steel reinforced concrete. And the entire building and all the magnets are on the same piece of floor to make it extra large and extra sturdy. Thank you, and I hope you enjoyed learning about our magnets.